Hey guys, this is Zainali and I am back with a new tutorial. This tutorial we will be discussing a problem regarding built-up section. So guys, before that, if you haven't yet subscribed to my channel, do subscribe my channel and click on the bell icon to get the notification about the newly uploaded videos. So here we have been asked to determine the radius of gyration about the centroidal x-axis for this built-up section. And the properties of the standard rolled steel sections has been mentioned here. So we will be utilizing this for determining the moment of inertia first, and afterwards by using the relation between the moment of inertia and the radius of gyration we would be determining the radius of gyration. So we would be solving this problem in the 4 steps only that we have discussed in the previous tutorials, the same steps that we are using for solving the problem regarding how to determine the moment of inertia for the plane lamina. So the first step is to draw the axis parallel to the axis, or draw the axis about which the moment of inertia has to be determined. So here about the centroidal x-axis we need to determine the moment of inertia. So first of all, let us draw the axis. So this is nothing but the centroidal x-axis. Now the next step is to locate the origin, which will be lying at the leftmost and the bottommost point. So here the leftmost is this and the bottommost is this. So somewhat the origin will be lying at this point. So this is considered as an origin having the coordinate 0, 0, and all the distances will be measured from the origin only. Now we need to split this entire built-up section into the standard sections, that is either channel section, beam section or angle section. So let us split this entire built-up section into the standard sections. So let us consider this as 1, this as 2, and this angle section is 3. And we need to locate the centroid with respect to that of the origin for each of these standard sections. So for the beam section, that is I section, the centroid will be lying at a half of its depth from the base or from the top. So let us draw the centroidal x-axis for this beam section and let us name it as 1, 1, and it is lying at a distance of 25 cm from the bottom. As we have discussed in the previous tutorial, whenever there is no unit mentioned we need to consider it as mm only. So the overall depth is 50 mm, so it will be lying at a distance of 25, overall depth is 50 cm, so it will be lying at the distance of 25 cm from the bottom. So this is 25 cm and this is nothing but y1. Now for the channel section, this is web, and for the channel section the axis which is parallel to the web we need to consider it as yy axis that we have discussed in the previous tutorial. First of all, let us draw the axis which is passing through the centroid for the channel section and let us name it as 2, 2, and this distance is nothing but cyy, as this is the yy axis for the channel section, as the standard position for the channel section is somewhat like this, and parallel to the web it is yy axis, and the location of the yy axis is given as somewhat cyy. So this is cyy, so here also this much distance will be cyy only. So the location of the centroid from the origin will be nothing but this much distance, and this is nothing but y2. So this is y2, and the value of y2 is nothing but nearly 52.2 cm. As for the channel section, cyy is given as 2.2 cm. The overall depth for the beam section is 50 cm. So 50 plus 2.2, so the value of y2 comes out to be 52.2 cm only. Now for this angle section, the axis which is parallel to the smaller one, that means parallel to this, is x-axis only. So this is x-axis only, and it will be lying at a distance of cx from the base. So this much distance will be cx from this base, but we need to consider the centroid location from the origin. So this much distance, that is the location of the centroidal x-axis for the angle section, that is 3, 3, from the origin will be nothing but y3 only. So this will be y3, and the value of y3 can be given as the thickness of the flange. For the beam section, the thickness of the flange is 1.72 centimeter. So 1.72 plus cxx for the angle section, that is 3 centimeter. So y3 will be nothing but 4.72 centimeter. This will be 4.72 centimeter. Okay. Now let us note all the values that we have determined. So for the figure number 1, that is for the beam section. So for 1, the value of A1 is nothing but 110 centimeter square that we have been already given. The value of Y1 that we have determined as 25 centimeter. For figure number 2, the value of A2 is nothing but 45.64 centimeter square. The value of Y2 is nothing but 52.2 centimeter. For the figure number 3, the value of A3 is nothing but 14 centimeter square, and the value of Y3 is nothing but 4.72 centimeter. Okay. Now we need to locate the centroidal x-axis axis, which is lying at a distance of y bar from the origin. So this much distance is y bar. So let us locate y bar, or let us determine the y bar. So y bar can be given as a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. We know all the values, so placing the values, you will be getting the value of y bar as somewhat 30.64 centimeter. Now we need to determine the moment of inertia of these standard sections above this axis x-axis. So Ixx1, we are applying the parallel axis theorem. So Ixx1 is nothing but the moment of inertia about the local x-axis plus area into the square of the distance between the two axes. So for the figure number 1, the distance between the two axes will be somewhat y1 minus y bar. So h1 is nothing but y1 minus y bar. We can also write as y bar minus y1, and Ixx1, that is given as 4.5 into 10 raised to 4. So 4.5 into 10 raised to 4 plus a1, that is 110 into y1 minus y bar whole square, and y1 is nothing but 25. So 25 minus 30.64 whole square. So we will be getting the value of Ixx1 as somewhat 4.85 into 10 raised to 4 centimeter raised to 4. Now we need to determine the value of Ixx2, and it can be also given as Ixx2, that is moment of inertia about the local x-axis plus a2 into h2 square, and h2 is nothing but y2 minus y bar. Okay, and Ixx2, and for the channel section, here it is y axis, so actually it is y axis, so Iyy2 plus a2 into h2 square. So here Iyy is nothing but 310.8 centimeter raised to 4. Here we are considering the y axis, as for the standard position this is y axis only. So we need to take the moment of inertia about this y axis only, and not about the x axis. This thing we need to remember. So Iyy2 is nothing but given as 310.8 centimeter raised to 4 plus a2, that is 45.64. So 45.64 into y2 minus y bar whole square, and the value of y2 is 52.2. So 52.2 minus y bar, that is 30.64. So 30.64 whole square. So we will be getting the value of Ixx2 as somewhat 2.15 into 10 raised to 4 centimeter raised to 4. Similarly, we need to determine the value of Ixx3. So it can be determined as Ixx3, that is nothing but equals to Ixx3, that is the moment of inertia about the local x-axis plus a3 into h3 square, and Ixx3 is nothing but moment of inertia about the local x-axis, and for the angle section it is given as 110 centimeter raised to 4. So it will be 110 plus a3, that is 14 into h3 square, that is distance between these two axes, and it is nothing but y3 minus y bar. The value of y3 is 4.72. So 4.72 minus y bar, the value of y bar is given as 30.64. So 30.64 whole square. So we would be getting the value of Ixx3 as somewhat 9.5 into 10 raised to 3 centimeter raised to 4. the total moment of inertia about the x-axis can be given as ixx1 plus ixx2 plus ixx3. We know all the values, so placing those values we will be getting the value of ixx as somewhat 7.95 into 10 raised to 4 centimeter raised to 4. But we need to determine the radius of gyration about the centroidal x-axis, and we know the relation between the moment of inertia and the radius of gyration is kxx is nothing but under root of ixx divided by area. Ixx that we have determined as 7.95 into 10 raised to 4, so 7.95 into 10 raised to 4 divided by total area, that is A1 plus A2 plus A3, and it is nothing but 110 plus 45.64 plus 14. So we would be getting the value of kxx as somewhat 21.64 centimeter. So guys, we have obtained the value of radius of gyration about the centroidal x-axis as 21.64 centimeter. So guys, that's all from my side. If you have any doubt, do comment in the comment section, and thank you guys for watching this video.